Okay. Okay. Let's get reading. It's hard to get comfortable. 2 pages. 2 pages. Okay. I just end up ripping my book. I'm so hard on my books. I can't. It's just so uncomfortable. Okay. I'm going to go through this figure. Figure 1.4, Fahrenheit and Celsius equivalent temperatures. Temperature of Earth's core, 10,800 degrees Fahrenheit, 6,000 degrees Celsius. Oxyacetylene torch flame, 6,300 degrees Fahrenheit, 3,480 degrees Celsius. Natural gas furnace flame temperature, 3,542 degrees Fahrenheit, 1,950 degrees Celsius. Air acetylene torch flame, 2,700 degrees Fahrenheit, 1,483 degrees Celsius. Pure water boils at sea level at 212 degrees Fahrenheit, 100 degrees Celsius. Average body temperature, 98.6 degrees Fahrenheit, 37 degrees Celsius. Pure water freezes at 32 degrees Fahrenheit, 0 degrees Celsius. Boiling temperature of R410A at 0 psig, minus 61 degrees Fahrenheit, minus 52 degrees Celsius. Surface temperature of dry ice, minus 109 degrees Fahrenheit, minus 78 degrees Celsius. Liquid nitrogen, minus 321 degrees Fahrenheit, minus 196 degrees Celsius. Absolute zero, where molecular motion stops, minus 460 degrees Fahrenheit, minus 273 degrees Celsius. For example, if we had a Celsius temperature of 20 degrees Celsius, we can determine the equivalent Fahrenheit temperature by plugging in the Celsius value into the formula to get degrees Fahrenheit equals brackets 1.8 times degrees Celsius, close brackets, plus 32 degrees. Degrees Fahrenheit equals brackets 1.8 times 20 degrees Celsius, close brackets, plus 32. Degrees Fahrenheit equals 36 degrees plus 32 degrees. Degrees Fahrenheit equals 68 degrees. So 20 degrees Celsius equals 68 degrees Fahrenheit. If we have a Fahrenheit temperature that we want to convert to Celsius temperature, we can use the following formula. Degrees Celsius equals brackets degrees Fahrenheit minus 32 degrees, brackets closed, divided by 1.8. For example, if we had a Fahrenheit temperature of 50 degrees Fahrenheit, we can determine the equivalent Celsius temperature by plugging the Fahrenheit value into the formula to get degrees Celsius equals degrees Fahrenheit minus 32 degrees, close brackets, divided by 1.8. Degrees Celsius equals brackets 50 degrees Fahrenheit minus 32 degrees, close brackets, divided by 1.8. Degrees Celsius equals 18 degrees divided by 1.8. Degrees Celsius equals 10 degrees. So 50 degrees Fahrenheit equals 10 degrees Celsius. Up to this point, temperature has been expressed in everyday terms. It is equally important in the HVAC/R industry to refer to temperature in engineering and scientific terms. Performance ratings of equipment are established using absolute temperatures. Performance ratings allow for easy comparison among equipment produced by different manufacturers. The Fahrenheit absolute scale is called the Rankine scale, named for W.J.M. Rankine, And the Celsius absolute scale is known as the Kelvin scale, named for scientist Lord Kelvin. Absolute temperature scales use 0 as their lowest value and start where molecular motion starts. For instance, 0 on the Fahrenheit absolute scale is called absolute 0, or 0 degrees Rankine. Similarly, 0 on the Celsius absolute scale is called absolute 0, or 0 degrees Kelvin. Figure 1.5. A Fahrenheit and Rankine thermometer is A, and B is a Celsius and Kelvin thermometer. So with the Fahrenheit Rankine, water boils at 212 degrees Fahrenheit, which is 672 degrees Rankine. Water freezes at 32 degrees Fahrenheit, which is 492 degrees Rankine. Water, I don't get that. Water freezes. Okay, I don't get that. Molecular motion stops at minus 460 degrees Fahrenheit. 0 degrees Rankine. Okay, over to the Celsius Kelvin scale. 100 degrees Celsius is 373 degrees Kelvin. That's where water boils. Water freezes at 0 degrees Celsius. It's just 273 degrees Kelvin. Molecular motion stops at minus 273 degrees Celsius, which is 0 Kelvin, 0 degrees Kelvin. 1.3 Introduction to Heat. The laws of thermodynamics can help further our understanding of heat. The first law of thermodynamics states that energy can be neither created nor destroyed, but can be converted from one form to another. This means that the production of heat energy is actually the conversion of other forms of energy, such as fossil fuels, gas, and oil. Temperature describes the level of heat intensity with reference to absolute 0, which was discussed earlier. The term used to describe the quantity of heat energy or heat content is the British Thermal Unit, BTU, which indicates how much heat energy is contained in a substance. The rate of heat transfer can be determined by considering the time it takes to transfer a certain amount of heat energy. Air conditioning and heating equipment is rated in BTUH, where the H represents hour. For example, an air conditioning system operating at a rated capacity of 24,000 BTUH has the ability to remove 24,000 BTUs of heat energy from the structure every hour. The BTU is defined as the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. For example, when 1 pound of water, about 1 pint, is heated from 70 degrees Fahrenheit to 71 degrees Fahrenheit, 1 BTU of heat energy is absorbed into the water. Figure 1.6. 1 British Thermal Unit, BTU, of heat energy is required to raise the temperature of 1 pound of water 1 degree Fahrenheit. And you can see that. When a temperature difference exists between two substances, a transfer of heat between the substances will occur. The next 3 sections in this unit address 3 common types of heat transfer, namely conduction, convection, and radiation. The temperature difference between the 2 substances is the driving force between heat transfer. The greater the temperature difference, the greater the heat transfer rate. Heat flows naturally from warmer substance to a cooler substance. Rapidly moving molecules in the warmer substance give up some of their energy to the slower moving molecules in the cooler substance. The warmer substance cools because the molecules have slowed. The cooler substance becomes warmer because the molecules are moving faster. So the next time you pour some warm soda into a glass filled with ice, remember that the ice isn't making the soda cold. The soda is making the ice hot. The following example illustrates the difference between the quantity of heat and the level of heat. Consider a tank that contains 10 pounds of water at room temperature, which is about 70 degrees Fahrenheit. If the water tank is to be heated to 170 degrees Fahrenheit, 1,000 BTUs of heat energy must be added to the water. 100 degrees times 10 pounds equals 1,000 BTUs. Now consider a tank that contains 100,000 pounds of water at room temperature. If the water in this tank is to be heated to 170 degrees, then that means 10 million BTU of heat energy must be added to the water. 100 degrees times 100,000 pounds equals 10 million BTUs. Figure 1.7. More heat energy is required to heat larger amounts of substance. We got small thing of water, big thing of water. So even though the initial and final temperatures are the same in both situations, the water in the larger tank contains much more heat energy than the water in the smaller tank. In addition, the water in the larger tank will cool down much slower than the water in the smaller tank. This is because there is much more heat energy stored in the water in the larger tank. Another water-related example may be helpful in differentiating between the level of heat intensity and quantity of heat. Consider a 200-foot deep well in a large lake with a water depth of 25 feet. Although the level of water is higher in the well than in the lake, these depth measurements cannot be used to determine the quantity of water present in either the well or the lake. The depth of water in feet tells us the level of water, but in no way expresses the quantity, gallons of water. In a similar manner, temperature relates to the level of heat, not the quantity of heat energy. Okay, that's 13 minutes. We got 2 pages read. Cool.